Okay, so Jim, just so you're aware, we are officially live on YouTube now.
Okay.
Thank you to everyone who is already watching. We're going to wait the minute until it's officially 7 o'clock to start to give others time to filter in. But thank you all for being here with us tonight to learn about the geology of the Lakes region. Okay, well, we are officially at 7 p.m., so I think we can get started. My name is Caroline Hughes. I'm a biologist at the Loon Preservation Committee. So thank you all for joining us for this summer nature talk. This is a series that we put on each year to help fulfill our mission of not only hands-on doing work to monitor and manage loons, but also to educate people about loons specifically, but also the natural world in general. And so tonight our speaker is Jim Vernon, who's going to be talking to us about the fascinating geologic history of the Lakes region of New Hampshire. Jim, thank you so much for being here with us tonight. I'm really excited to hear your talk, and you can take it over whenever you're ready.
All right, thanks, Caroline, and thanks everyone for Zooming in. This is the first time I've done it this way, so we'll see how it goes, but I do appreciate those that are watching. And so we'll get right into it. I'm going to be talking about the geology of the Lakes region, as Caroline said, and happy to take questions. I guess there's a mechanism through YouTube for that. So here we go. So I don't need to tell you that we live in a beautiful part of the world, looking up at Whiteface Mountain here from Sandwich. So as geologists, we look at the landscape and we're interested in how did the landscape get to be the way we see it today. There's Bald Knob, one of the Ospey Mountains. To a geologist, the Ospies are very different geologically from the White Mountains to the north, like Whiteface that I just showed you. So looking south from almost the same place that I took the first picture, there are the Ospies. They might look similar at first, but we'll see that the geology that formed these mountains is very different. Everyone who lives in New Hampshire has walked through the woods and seen stone walls, but if you look closely at them, you see several things, and you don't need to know the names of the rocks or to be an expert to make some interpretations. If you look closely, chances are in most stone walls, there are a variety of different rock types. Also, you'll notice they're somewhat rounded. They don't have sharp angles in them, so they didn't just fall off a cliff. They've traveled some distance to get worn down and rounded off. So there's a story right there. You see different types that probably came from different places. So as geologists, we ask, how did they get there? Other than the farmer getting them out of the way of his field to build a stone wall. But how did they get to that general area? And how did they get rounded off? And why are they of such different types? So if you look more closely, you can see there are differences in color and in texture. And again, you don't need to know the names of all the minerals to tell a story. A lot of these rocks are igneous rocks, meaning that they were once very hot, ignited, fiery hot, and then they cooled off. So if you look at the size of the crystals, you can tell how quickly or slowly they cooled off. Obsidian or volcanic glass that you may have heard of, you can't see the crystals. That cooled off very quickly. It's probably lava that erupted to the surface. The rocks I'm showing you here, you can see the minerals, the feldspars and quartzes. You can see the crystals. They cooled more slowly, allowing the crystals time to form. So even if you don't know what the rock is called, you can tell a story by looking at it. If it cooled slowly, that means it was deep underground. Now it's at the surface. So there must have been tremendous upheaval to bring it to the surface. Then it had to travel to get rounded off. It had to be rolled or dragged or pushed across the ground. And then some farmers or other folks put them into a stone wall. Some rocks travel tremendous distances, even though they're very large. This is Madison Boulder, which you may have seen if you've driven up Route 113 in Madison. There's a turnoff to it. And this rock you can't see from the picture, but it's in a valley. It's not near the bottom of a cliff. It's in a broad stream valley. No other rocks like it nearby. How did it get there? Certainly wasn't dragged there by people. So this is the kind of questions that we ask as geologists. Or you may be hiking in the White Mountains, and I'll take some liberties with the Lakes region and extend up to the mountains. You may see a quartz rock along a ridge in the Whites. It looks very different from most of the darker schists and other rocks that you see in that area. How did it get there? It's not in a valley. A river didn't wash it there. How would it get up on the crest of a ridge like that? Or you might see potholes. These are formed when smaller stones get swirled around by running water. And you can imagine if there's enough time, you can see how the grinding action could make a round pothole. The only trouble is this particular one is on a ridge. It's on the Caps Ridge Trail going up Mount Jefferson. Some of you may know it. So how did you get running water on the crest of a ridge, on a ledge up there? Well, you can see the power of running water, and you can see how a pothole could form under this energy. But as I said, how would it form up on a dry spot that's now on top of a ridge? Also, the point I want to make here is that geology is not a dead action in the past. The earth is still changing, erosion is still going on, the earth's wearing away, volcanoes are still erupting, so it's a dynamic process. One of the reasons I got into geology is because I like maps, and geologists like to make maps. This is the older geologic map of New Hampshire, and I'm showing it to you instead of the newer one because it's easier to see the patterns. In the western part of the state, you see the colors, each color representing a different rock type or rock formation. They form kind of a linear pattern, these bands of different rock types that follow more or less the Connecticut River. These are metamorphic rocks, and we'll get into that a bit. And they are layered. Different rock types occur in these different north, east, southwest trending layers. Then you see these pink blobs, especially in the eastern and central part of the state. These are the igneous rocks that have intruded into the metamorphic rocks. The igneous rocks were rocks that were once melted, and they've risen sometimes as volcanoes, more often as molten magma beneath the surface that then cooled off and was later exposed. You might see towards the lower right of your view Lake Winnipesaukee there with a circular pink spot just to the north of it. Those are the Ospey Mountains that I mentioned. And the south edge of the lake, you see the Belknap Mountains. We'll be talking more about those later. Then we look at our lakes. We're in the Lakes region. This is actually near Weirs Beach. And I know sometimes sand is trucked into the beach, but most of this is natural. How did the sand get there? Another question. We're questioning why, we geologists. It's interesting to look at sand to see what it's made of and to see how rounded the grains are. the more rounded the grain is, the longer it traveled. We think back to the ice ages, which I've alluded to, and we see that the climate is still quite variable. This is Squam Lake. Usually it melts before May. This particular year, there was still ice in May, but the climate has always fluctuated. Of course, human beings are accelerating climate change, but we're going to talk more about climate fluctuations and how it affects the landscape of the Lakes region. So we're going to talk about roughly 5 billion years of Earth history. Geologists think the Earth is somewhere between 4.5 and 5 billion years. And those numbers are pretty hard to contemplate, I think. So what we're going to do is pretend those 5 billion years actually were in 1 year, 12 months, 365 days, and see when different events that shape the Lakes region happened. So we're going to compare it to 1 year. So starting with New Year's Day, 5 billion years ago, that's when the Earth was formed. So we're going to go to March and April before we even find any rocks that we can date as that old. And they're not in the Lakes region. I think they were found in Australia. The oldest known rocks, last time I checked, are 3 to 4 billion years old. And they date these using radioactive dating. So we're going to skip right ahead to September 1st, a billion years ago in the late, what geologists call the Precambrian time period. By this time, there was fossil evidence of ancient invertebrates. So we know there was animal life, plant life probably occurred beforehand. It's harder to fossilize plants because they're soft. I was just reading an article yesterday about a geologist in Canada who found fossilized sponges that are 890 million years old. So those are among the oldest animal fossils that have ever been found, but they're not in the Lakes region. So we're going to skip ahead to December, 395 million years ago, or the early Devonian period. And these time periods are named by geologists based on areas of the world where rocks of that age were studied, in this case, Devonshire in England. At this time, we know that the Lakes region was covered by ancient seas. And we know this because we can tell that the sediments that were deposited that are now in rocks were composed of mud, sand, and lime. And these are deposits that are formed in water. And believe it or not, there are a few fossils that have been found in New Hampshire. Most of them have been cooked, as I'll explain, but they have found some fossil shellfish in rocks of this age. So we believe that New Hampshire is covered by an ocean at this time. Few marine fossils have been found, as I mentioned. Sediments that were deposited piled up in layers, and the pressure of the layers squeezed them into rocks, which we call sedimentary rocks, shale, sandstone, and limestone being 3 of the most common. Moving ahead to December 6th, now we're at 350 million years ago in the mid to late Devonian period. We had what's called an orogeny, which is an episode of mountain building, tremendous pressure and heat in the Earth's crust, altered the rocks, heaved the rocks up. The sedimentary rocks were cooked, recrystallized, and squeezed, and they became schists, gneisses, and slates instead of sandstones, shales, limestones, etc. An example of this, one of the most common rock types in the state, is the Littleton Formation, named where it was first described in Littleton, New Hampshire. And that actually is the rock where they found a few fossilized shells that didn't get completely destroyed during this mountain building episode. Also, we had igneous rocks, which formed from molten lava. The New Hampshire Plutonic series formed at this time. And I'm sorry to throw so many terms at you, but plutonic refers to igneous rocks that cooled underground, as opposed to lavas, which erupted to the Earth's surface. And just a few of the formations that are particularly common around here, the Kinsman quartz monzonite, which I'll show you pictures of, and the Winnipesaukee quartz diorite, which is a dark rock that's found all around Lake Winnipesaukee, not everywhere, but many places. So here's a picture of the Kinsman quartz monzonite. It's distinctive because it has these white blobs of feldspar. And I call it the 55-mile-an-hour rock because you can see it. You can see those white blobs while you're driving by in your car. The picture on the right is taken on Route 104 between Meredith and New Hampton. So several outcrops along there are of this rock type. It's similar to granite, but not quite the same. And then you see the formation I mentioned, the Littleton schist. It looks quite blocky here. This is a part of it that was originally probably a sandstone before it got squeezed and pressurized and recrystallized to schist. Some of it is much shalier, slatier, weaker rock, but it's usually a dark gray to a light gray, sometimes a lot of shiny mica in it. And you see it up and down I-93. Sometimes it's rusty looking because of the iron in the rock. So I've told you, I've thrown a few terms around, so just quick summary. Sedimentary rocks are formed of sediments. They're piled up in layers, oftentimes in marine seas, but not always. They can form in rivers and lakes and other settings. Sandstone, limestone, and shale are examples of them. There are no longer any in New Hampshire because any that were here got cooked or melted or squeezed and metamorphosed. Other parts of the country, out in the Midwest, they can form excellent aquifers. Water can be stored in between grains of sand in a sandstone or in caverns in a limestone, but we don't have any of that here. Then there's igneous rocks that I've mentioned. Igneous, I think of the word fire when I see that. So these are rocks that were so hot they were melted. And they can be either plutonic, magma underground that was molten and then cooled gradually, or volcanic, which is molten rock that erupted to the surface, like in Iceland or Hawaii. These can form aquifers only if they're fractured. They're solid rocks. They're common in New Hampshire. In fact, we're called the granite state, and granite is an example of an igneous rock. These cannot store water between the grains. The crystals interlock. So you can get water from them only if there are cracks or fractures in the rock. And many people that have drilled wells in their houses, that's where they get their water, from the cracks in these igneous rocks. Or in the third type of rock, which we also have in New Hampshire, metamorphic. These are rocks that were changed, and they started out as either sedimentary or igneous. Then they got compressed and heated during these mountain building episodes, not enough to melt them, but enough to recrystallize them. And nice schist, slate, marble, these are all examples. And they can also form aquifers, but again, the water can only move through the cracks or the foliations or layers in the rock. They're very common in New Hampshire. So moving back to our Earth history in a year, we're up to December 15th now. 225 million years ago, this was the beginning of what we call the Triassic Period. And this was the age of dinosaurs. There are no dinosaur fossils found in the Lakes region, but you don't have to go too far. If you drive south on I-91 through Vermont down into Massachusetts and southern Mass and down into Connecticut, you may see red rocks along the road. These are the rocks from this age. These are sedimentary rocks that are younger than the mountain building episodes, so they never got cooked, they never got metamorphosed, and they were formed in rivers and sandbars and lakes and so on. They weren't under the ocean. So these were terrestrial rocks, and the dinosaurs walked across those sands before they became sandstones, and in some cases left footprints. So if you're ever traveling to Connecticut, I recommend Dinosaur State Park, which is south of Hartford and not far from the interstate. And you can see the dinosaur tracks in the rock that they uncovered when they were building an office building. And the backhoe operator realized he'd found something special. So he stopped construction. The state bought the site and made it into a state park. So if you want to see dinosaur footprints, that's a good place to go. This was a time when the North American and Eurasian plates, and you've probably heard of plate tectonics, were splitting apart. We had been one giant landmass, but this was a rifting time, and it caused faulting and fracturing in the rocks that were already there. And these red Triassic rocks filled in some of the low basins that formed. In the Lakes region, however, it was a time of uplift. Rocks that had been formed under the sea were lifted up and eroded. Skipping right ahead to December 18th, we're now at 180 million years ago, what's known as the Jurassic Period. Still in the age of dinosaurs, and this was the time the first birds evolved. We know this from fossils elsewhere. There aren't any in the Lakes region. There was a lot of action in New Hampshire at this time, though. Another mountain building period and a series of igneous plutons were formed at this time, younger than the earlier ones I told you about. And some of these formations are the Albany quartz syenite, Conway granite, the Mountain volcanics. There actually were volcanic eruptions in New Hampshire at this time. And you can see volcanic rocks from these lava flows if you go up to Castle in the Clouds. If you walk around outside the castle building, you're on volcanic rock there from these mountain volcanics. This is the time when these circular ranges, and remember I showed you that on the geologic map of New Hampshire at the beginning, formed during this time. The Ospey Mountains, Red Hill, the Belknap Mountains, farther south, Mount Pawtuckaway, and farther north, the Pilot Range. These are all these circular volcanic features that formed during this time, the Jurassic Period. So here's a picture of the Albany quartz syenite. It's one of the igneous rocks that formed during this time and is part of the Ospey Mountain Ring Dike complex. This outcrop is found on Ossipee Park Road. It's not particularly safe to park there because the water trucks go up and down from Castle Springs. But you can park lower up or higher down, or lower down or higher up, and walk down the road and see these rocks. And they're unusual. You don't find them other places. This particular one with the pale, spotty look is typical of the Ospey Mountains. Mount Roberts is formed on part of the Ring Dike. It's, as I say, a circular mountain range going around the mountains, and it's a nice hike up there. Also, you can see a very interesting feature called columnar jointing that forms in some of these volcanic rocks. The way they cooled off after they erupted formed cracks. Sometimes you get these almost perfect hexagonal columns that form like that. So these are found in the Ospey Mountains and other places in the world, but they're typical of volcanic rocks. So it gives you an idea. You know, Hampshire is pretty quiet geologically now, but that wasn't always the case. There's a lot of action going on in the past. As I mentioned, you don't need to be a professional geologist knowing all the terms to tell a story. Here, first you see a light rock on top of a dark rock, so that tells you something about the changes in the environment where the rocks were formed. But then also you see chunks of the dark rock contained within the light rock. The light rock is an igneous rock, and as the molten rock was flowing through the cracks underground, it broke off and picked up chunks of the darker rock that were probably beneath it. So it was hot, but not hot enough to totally melt the other rock. So you can tell a story even without knowing what they're called. So just to summarize, and by the way, there'll be a quiz next week, so I hope everybody's taking notes. The Littleton Formation we've mentioned, one of the most common rock types in the state. You can see it in many places. A darker rock, Winnipesaukee quartz diorite, is one of those igneous rocks, but it's plutonic, it cooled slowly. Underlies much of Lake Winnipesaukee and surrounds much of the lake. Then the lighter rock, the Kinsman Quartz monzonite that I showed you along Route 104, you can see it along Route 3 also near Little Squam Lake. Conway granite, the famous redstone quarries up in Conway were mining this type of rock. It's also present in the Ossipes and the Belknaps. It's one of the younger igneous rocks. Then I showed you the Albany quartz syenite, which forms part of the ring dike. The Moat Mountain volcanics, which you can see at Castle in the Clouds. And then there are these pegmatites, which are these beautiful dike rocks with large crystals because they cooled off very slowly. Ruggles Mine, which I don't believe is open anymore, but some of you may have been to, mined these pegmatites, and they're very large crystals, a great place to rock hound if you can get in. So just to mention a few of the minerals you've probably heard of. Quartz, the clear, hard mineral used for sandpaper. Feldspar can be confused with quartz, but it's usually opaque and can be various colors, tan, pink, sometimes even blue. And then you've heard of the micas, the muscovite, the clear mica, and the biotite, the black mica. And then there are other dark minerals like hornblende. So again, you don't need to know all these names to tell a story with the geology, although some people love to identify them and collect them and so on. So we've talked about the Ossipee Mountains, and they are unique to this part of New Hampshire. There are other ring dike complexes in the world, but this is considered one of the most perfect rings in the whole world. And it's a somewhat complicated history. And there's still research going on about how the Ossipee Mountains formed. But there's kind of a sequence here, and geologists have worked out sort of the steps, the order in which they think things happened. So I'm not going to talk all the way through this, but you see that it was quite a series of steps, followed at the end by glaciation, which we haven't really talked about yet, but we will be. And here's kind of a schematic going from top to bottom. It's a sort of a time series cartoon of how they think the Ossipee Mountains formed. And those outer ridges that you see in figure E at the end form the current ridges that you see today. And it's actually, the Ossipees are lower in some parts of the center than they are around the edge. You think of Danhole Pond, if you've ever been there in Ossipee, that's inside the ring, so it's a little lower than the ridges that surround it. But it's almost a perfect circle. There are other ring dikes, but very few are as completely circular as the Ossipee Mountains. Another example, not as perfect, if you will, is the Belknap Mountains south of the lake. And you can see they're not quite circular, but they have a circular pattern. And some of it extends out to the islands in the lake as well. So that makes it a little different from the Ossipes that is partly submerged. And again, we won't go through the details, but you do see the Moat Mountain volcanics also occur down here as one of the rock types. And here's a sequence of events for how they think the Belknaps formed. Again, going from A to F, starting with just flat layers of rock and with various volcanic eruptions, metamorphism, erosion, step-by-step sequence of how they think it formed. Geologists like to tell stories, and the good thing about it is no one can go back millions of years in the past to prove us wrong. So we can we can tell stories, although there is indirect evidence that might favor one interpretation over another. But a lot of these things are open to interpretation, and reading the landscape or looking at the rocks and trying to discern how they got there, I think is one of the interesting aspects. We're going to jump way ahead now to New Year's Eve. In fact, 8 p.m., only 4 hours before midnight, if the history of the Earth were compressed into 1 year. About 2 million years ago, the start of what we call the Pleistocene epoch. At this time, the ice ages began, and you've heard of the ice ages, I'm sure. Also, this is the time when human beings evolved. No fossils of humans in the Lakes region at this time. And you think about ice ages, it doesn't take a lot to start an ice age. Even in the White Mountains on Mount Washington, which you're seeing here, the one in the clouds, this picture was taken, I think, in May of this year. They've recorded snow every month of the year. Now, when snow is in the summer, of course, it melts away, but it wouldn't take too much of a shift to get some of the snow to stay year-round. And then if more snow falls the next year and stays, eventually it builds up and gets thick enough to form a glacier. And the pressure of the glacier can melt some of the ice or snow at the bottom and lubricate it, and then it starts moving. So wetter as much as colder conditions are required to start an ice age. And geologists from the record in North America believe there were actually 4 different pulses of glaciers advancing across North America and then retreating. So moving up to 2 minutes before midnight, or about 19,000 years ago, this is the time when the last of those 4 pulses covered New Hampshire. Ice covered all of New Hampshire, in fact, all of New England, and extended down as far as Long Island and Cape Cod. And those features are actually what we call moraines, gravel, sand, clay, hodgepodge of material that was bulldozed by the glacier. And that's how Long Island, Cape Cod, Martha's Vineyard, Nantucket, that's how they were formed. It was material that the glacier scraped off the ground as it flowed past, albeit slowly. And then when the glacier reached its southern extent, it was still moving, but was starting to melt. And all that gravel, sand, rock, clay, whatever, was dropped out of the ice or bulldozed in front of the ice and left there, forming Long Island, Martha's Vineyard, Nantucket, Cape Cod. Here's Mount Washington with Lakes of the Clouds in the foreground. For a while, people thought that the summit of Mount Washington might have stuck above the ice during the glacier, that the ice age, filled the valleys and the lower hills, but the highest summits like Mount Washington, they thought probably stuck above the ice. But close look at the boulders on the summit, some geologists recognized some fairly unique rock and mineral types and identified a location several miles to the north, which is the nearest place where that rock outcrops as bedrock. The only way naturally that a boulder such as that could get to the summit of Mount Washington is by the ice age. A river couldn't wash it there. And so it has been pretty much agreed that the ice age, the glacier, covered everything in New England, including the summit of Mount Washington. Other evidence for glaciers, you can imagine when the idea was first brought up, there were skeptics. People didn't believe that the entire state of New Hampshire, all of New England, could have been covered by ice. I mentioned the Ospey Mountains, also Red Hill. It's a smaller version having some unique rocks like this Albany quartz syenite, that sort of tannish one I showed you a picture of. Those rocks aren't found anywhere else in outcrop, in a ledge, other than in the Ospey Mountains and Red Hill. and maybe a couple other places. People actually studied stone walls and made counts of the different types of rock that are found in the stone walls. And these unique rocks that are found in the Auspice and Red Hill are pretty common in stone walls to the south and east, but they're just about virtually absent in other directions. The only reason, and a river couldn't wash a rock from a cliff or a mountain down, way down into the valleys if you're not in a river valley. So that was an evidence for the glacier. They think the glaciers overrode the mountains, plucked off pieces of rock off the cliffs in the mountains and carried them downhill to the southeast. The glacier flowed from the northwest to southeast. So they've actually mapped out counts of rocks in stone walls and mapped these areas where these boulder trains occur. And sometimes these boulders are just lying loose in the woods. They weren't all put in stone walls. Another feature we see that you may have heard of is drumlins. We see these asymmetrical hills with the diagram on top. It's not a very good picture, but perhaps in the bottom you can see a gradual slope on the right-hand side and a steep slope on the left-hand side. This is attributed to the glacier moving from right to left, flowing up the hill and then plucking rocks off the downstream, in this case, usually the southern side, and forming a much steeper slope or cliff. Here's an example of one of these drumlins. Smooth, gradual slope on the right and a steeper slope on the left. So the inference is that Ice Age moved from right to left across this view. And you can see it up if you're hiking up in the White Mountains. This is a view of Mount Monroe from the south. You see a gradual slope on the north side or northeast side of the mountain and a steep, almost a cliff on the other side. So you would infer that the ice flowed from right to left in this picture, plucked rocks off the downstream side as it flowed over. The glacier did other things too. It formed glacial grooves. This, you can see this if you hike up Rattlesnake Mountain off Route 113 in Holderness. It's not too far up the trail. As you go up the trail, it's on your left. And these are not the layers of minerals. These are just grooves in the surface. And this is inferred to be formed by the ice flowing over the rock. The ice was like sandpaper because it had stones in it that it had picked up along the way. As it flowed over the ledge, it scratched these grooves into the rock. So this is another thing that's hard to explain any other way than the Ice Age flowed across this area. Some features that were formed by the glacier. One well-known one is the glacial cirque. This is King Ravine in the northern presidentials, Tuckerman's Ravine that everyone's heard of, Huntington Ravine. These are all examples of glacial cirques. They are different from stream valleys because they tend to be U-shaped in profile, whereas a stream valley, if it hasn't been glaciated, is typically more V-shaped with straight sides and steep at the bottom. These tend to be flat at the bottom with straight sides higher up. This is because it was formed by moving ice, not moving water. So the ice didn't down cut as sharply as water would in a river. So we're now 1 minute before midnight on our year, 10,000 years ago. This is the time the last ice age began to retreat. The climate warmed, the ice was melting. Now the glacier still was flowing to the south. The ice was in the glacier, was still flowing, but the margin retreated north because melting was happening faster than snow was falling in the winter. So when we say retreat, the ice didn't turn around and move, but it just started melting. So the front edge of it was moving back to the north. As all this ice melted, that water had to go somewhere. There were large rivers coming off the glacier, much bigger than the rivers we see today. Oftentimes, all the rock and gravel and clay that had been bulldozed ahead by the glacier formed a dam. So you get temporary lakes that sometimes lasted decades or even a century or more that formed behind these piles of debris that the glacier had left. The most productive aquifers for water wells in the state are formed of sand and gravel that were deposited by these large meltwater rivers. The rivers would carry away finer grained clays and silts and leave behind sand and gravel with spaces in between the grains that are now useful for storing groundwater. And the biggest wells that serve towns like North Conway and many others around the state are formed in these aquifers that formed as the ice was melting. You can imagine the glacier, as I said, covered all of New Hampshire, tended to scrape away most of the soil and loose material that was already there. So things were pretty barren as the ice retreated. Most all the soil that we see today is formed in the last 10,000 years since the ice retreated. And that's part of why a lot of the soil in New Hampshire isn't all that fertile. It's young, it's got a lot of quartz and sand in it. Some places it's good, but parts of the country that have never been glaciated often are easier for farming. Plants, of course, were totally killed and wiped out by the ice ages. So everything we see today in terms of plants and forests and meadows, bogs, all the plants recolonized since 10,000 years ago when the ice was retreating. Now, all that water that melted from the glaciers had to go somewhere. Well, it flowed in rivers, unless it was trapped in a lake, flowed down to the ocean, and sea level actually rose markedly during this time following the glacier. In fact, some of the present river valleys were flooded by seawater, and marine fossils have been found in clays as far upstream as Fryeburg, Maine, and well up in some of the river valleys in New Hampshire. So the sea advanced during this time, and we have fossils that are from shells that only live in salt water. So we're pretty sure of this interpretation. Another factor that happened, as you can imagine, when New England was covered by ice, it was very heavy. If it was thick enough to cover Mount Washington, it might have been a mile thick in some places. When that ice melted, it's almost like the Earth's crust breathed a sigh of relief. The crust lifted up as this weight was removed. So some of these areas that had been flooded by sea, as the land rose, the seawater drained back out, and they're now high and dry. As the glacier was melting, some very interesting features were formed. Remnants of ice were trapped in valleys after some of the hillsides had cleared. A lot of times, if you look in that upper picture, you see where it says stagnant ice. There would be tunnels formed under the ice, and meltwater rivers would flow through those tunnels. Other times, you had meltwater streams on top of the ice or beside the ice. And these streams carried sand and gravel and then deposited them as they flowed by. Once the ice disappeared, you see in the lower figure there, some interesting features formed. You may have heard of eskers, which are these long, sinuous, sandy, gravelly ridges. A lot of them are gone because they're very clean sands and gravels that were mined out for highway construction, but there are still some left. You also had terraces along the valley walls that formed from this sand and gravel called cames. So here's a cross section of an esker in a quarry. You can see the sort of the sharp ridge crest, and the sands and gravels are rounded and well washed, look like they were water washed, but for a long time people couldn't figure out why they would be formed on a ridge and not in a valley. you would think river gravel would be in a river valley. Eventually, the explanation that these were streams flowing under the glacial ice as the glacier melted could explain it. So here's an air photo view of one. This is south along Route 16. The Pine River Pond actually has an esker that runs through the middle of it. That saved that one from being mined out because it's in a lake. Here's another air photo view of the Pine River esker when it extends out of the pond onto the land. I think a lot of this is now gone. This is a very old picture, I think. I'm not sure when it was taken, in the 30s or 40s maybe. A lot of that's now disappeared. It was mined out for highway construction. But you can see one if you go to Purity Springs in Madison, and you stand near outside the building where the swimming pool is and look across the pond. You're looking right at the nose of an esker. That ridge is an esker. Pine trees are common on eskers because they can live in sandy soil where some of the other tree species don't do as well. And you can walk on it. There's a little path. This is running right along the crest of an esker. So if you go there and walk this, maybe you can picture yourself under several feet of ice in a river that was flowing under the ice, but now looks like a ridge. Also, as I mentioned, as the glaciers were melting, they did form some temporary lakes that got trapped behind barriers of gravel and temporary natural dams. This is Whiteface Intervale in Sandwich, looking up towards Mount Chicarawa, one of the few areas in Sandwich where people still farm. This is one of these glacial lake beds. While there was a lake there, it may have been a few decades or even a few centuries, you had quiet deposition of clays and silts in this lake water. Because there was no current, it didn't get washed away as it would have in a river. So this built up some fairly fertile soil and allows this area to be flat, unusually flat for New Hampshire. And you see still today some farming there. So as I mentioned, these glacial meltwater deposits account for most of the major sand and gravel deposits in the state. So it's economically valuable to be mined. And some of the features that formed, just to sum up, these cames, these are sand and gravel deposits made by meltwater flowing between the ice and the sides of a valley. So they're often plastered up against hillsides. You sometimes recognize them because they're favorite places to put cemeteries. The sandy soil is easy digging, and they're usually sitting up on the valley wall, so they're out of the water table. So sometimes a good way to tell a came is because there's a little old cemetery up on it on the hillside. I mentioned these eskers, these narrow winding ridges of gravel, and you can go to the Purity Springs if you want to see one. A lot of them are gone now, but there's still some of them around. And then general, you had layers of sand and gravel that got deposited by rivers of glacial meltwater that were much bigger than the current rivers. And some of them flowed in different places. And these form excellent aquifers. So you may see some of these deposits in areas where there are not rivers today, or you may see them along the banks of the Merrimack and some of our other rivers, because those rivers were bigger at the time and the water was flowing through. These features formed deposits that we see today. The glacier, as I mentioned, picked up all kinds of material: clay, sand, cobbles, boulders, picked it up from farther north, carried it, and then when it melted, it just fell out of the ice. This is a hodgepodge, covers most of the state, except if you're in one of these sandy areas or you're in a place where there's bare rock. Then I mentioned these eskers. We saw pictures of these rock drumlins. These are rounded hills that are aligned with the glacial flow direction, and they usually have steep sides on the down glacier side. Then we have these deposits of sand and gravel from glacial meltwater. They're widespread, there are lots of them, and they form excellent aquifers. And then sometimes these intervales, like Whiteface intervale or Wanalancet intervale, you come into these flat valleys where there may be hayfields or even farms. These were where the ancient glacier lakes were. They're temporary by geologic standards. They may have only lasted a few decades or 100 years. And that's a blink of an eye to a geologist. Lake Winnipesaukee also formed mostly post-glaciation. There certainly was water there. It was a lowland area, but we think rivers flowed through that area and not a lake until the glacier came. The glaciers moving from northwest to southeast scoured out the rocks in the Winnipesaukee Basin. They tend to be a lot of these igneous rocks. They were somewhat weathered and a little bit softer than the surrounding rocks like the Littleton schist. As the ice melted and retreated towards the north or the northwest, the present outlet at the Weirs Beach was dammed by ice. At that time, the lake had a lot more water in it. It was higher, and the outlet was at Alton Bay. If you drive Route 11 through Alton Bay, you look to if you're going east, let's say, you look to your left, you're right there, you see the lake. If you look to the right, it's a bit of a drop off, and it's kind of an empty valley. It's kind of marshy and swampy. It's not too hard to imagine the water from Lake Winnipesaukee rushing down in that direction. And that's what it did until the lake level dropped. As ice retreated, water then broke through at Paugus Bay and flowed down the present Winnipesaukee River, down through Laconia and down towards Tilton. The lake then dropped to its present level, although of course we control it by dams there in Lake Gore. So there's a view of the lake, and you can see that that's the result of the last 10,000 years. Most of our lakes formed since the ice melted. So I don't need to tell you we live in a beautiful area, but at least for me, it enhances it to have an idea of how it formed. I think this is the view from Rattlesnake Mountain, which many of you have probably climbed up Musquam Lake. Some other features, and as I say, geologic processes are ongoing. Maybe too slow to notice around here. Luckily, we don't have a lot of earthquakes or volcanic eruptions, but the earth is dynamic and still changing. This is King Ravine in the White Mountains. And as I mentioned, it's flat bottom because it's a glacial cirque, not a river valley. But you have this rock glacier. There are bent over trees that show us that rock glacier is slowly moving. So the earth is not fixed. Things are still happening. Erosion is occurring. You see exfoliation in some of these mountains. You see these curved cracks in the rock that are parallel more or less to the surface of the mountain. Eventually, these slabs of rock will break off. So erosion is still happening. We move ahead now to 1 second before midnight on our clock. About 170 years ago, Audubon painted the birds of America. And we're going to skip ahead to almost the present, and just, even though it's out of the Lakes region, I think the demise of the old man of the mountains is pretty interesting. So as we know, that was sort of the symbol of New Hampshire for many years, and it gave New Hampshire bragging rights over Vermont. One day, and I think it was 2003, I believe it was 2003, fell down. It fell down during the night. No one saw it. It was a foggy, rainy night. People noticed it the next time the weather cleared and they were driving down through Franconia Notch. There are some theories as to how it happened. And as you may know, it was precarious, known to be precarious, and it was held up by wires and cables for a long time. And in fact, there were people who dedicated themselves to hiking up to the top each year, making sure the cables were okay. But this little block diagram here gives an idea of how they think it happened. There was a cavity behind that lower block 5, so it was very precarious and sort of being held in place by the upper rocks. There were many theories as to what caused it to fall. People thought, maybe it was earthquakes, maybe it was traffic in the notch, maybe it was wind. I don't know for sure, but they did set seismographs up there, and they pretty much determined that it wasn't construction. You might remember when they put 93 through the notch, it was controversial, or some of you are too young to remember that, but some people thought that the rumbling of trucks through the notch may have caused it to fall down. But the seismographs didn't record much vibration from that, and wind actually may have played a bigger factor. Wet rainwater collected in those cracks and lubricated things. So I think it's time had come, and if it weren't held up by chains and cables, it would have happened a lot longer ago. So if you go up to Franconia Notch, they have a display now describing how they think the old man fell down. As I mentioned, changes are still occurring. The Earth's still dynamic, even here in New Hampshire. Some friends have some property in Sandwich. They got up one day after a rain and saw the whole banking beside their brook had caved in. So erosion certainly is still happening. It's usually gradual, but sometimes it's dramatic. So I encourage everyone to go out. You don't need to be an expert. You can make interpretations about the geology just by going out and looking. And you may be rewarded by a double rainbow, like I was one of the days I went out to take pictures for the talk. And that's the end. And if there's any questions, I'll do what I can to answer them.
Yeah, Jim, thank you so much for sharing your expertise with us. It's so cool to learn more about the history of the place that I live and work. So thank you. We do have some questions in the chat.
Okay.
The first is about our mountains here and the processes that have occurred here to make those mountains and that have happened since, and how those compare to the Rocky Mountains on the other side of the country.
Oh, great question. Generally, our mountains are a lot older than the Rockies. Some motion in the Rocky Mountains in some places might still be happening, but they are fault-bounded mountains. If you approach the Front Range in Colorado, say from Denver, from the east, they rise very abruptly out of the plains. Those mountains have risen along a fault with the western block being uplifted, and they're much younger. There certainly has been some erosion, but they haven't had time to get rounded off the way our mountains have. Our mountains are, hundreds of millions of years old. Although there's slow rise in some areas, the last real mountain building action, as I showed, was, over 100 million years ago. And so there's been plenty of time, and New England's been above sea level most of the time since. So it's been subject to erosion. So that's one of the big differences, is the age of the mountains and the time for our mountains to be worn down, not just by glaciers, but by wind and water and freezing and thawing and so
on. We also have a question about all of the mica that is around in New England and in the Lakes region. So it says, I'm wondering about all the mica. There is that now defunct Ruggles mica mine, and large flakes of mica are often seen in some sources of gravel. What's the story there? Where's all this mica coming from?
Good question. Micas are minerals that formed in metamorphic rocks that I mentioned early in the talk, and they started out as clay minerals. And chemically, different micas formed from different clays. And when the rocks were heated and pressured, not heated enough to melt, but heated enough to change the minerals, clay minerals, which are platy under a microscope, turned into micas. And whether you have a biotite, which is a black mica, or a muscovite, which is a clear or white mica, or some other types that are gold colored and can have different colors, those derived from clays because they formed under pressure and with some heat, but not enough to melt them. They tend to line up in the same way, forming in the same direction, forming these books, and sometimes make the shiny surfaces of these schist rocks that we see, because they're all pointing in the same direction, typically layered. So they're from clays and typically found in metamorphic rocks.
And then the last question is actually my question.
Okay.
So at LPC, we have what we call the Rock Rearranger Award, which is given each year to the field biologist who does the most damage to the boat propellers as they're out and about on the lakes. And so I've heard from people who are visiting from other parts of the country that our lakes are a lot harder to navigate than the lakes that, or the water bodies that they might have further south or just in other parts of the country. And so are all of these rocks that we are having to avoid and sometimes not having much luck avoiding, are those glacially deposited as well for the most part?
Most of them, yes. Some of them might have broken off ledges or outcrops of bedrock directly. But most of the rocks, especially if they're rounded, if you see a rock that's rounded, it's been tumbled, it's traveled a distance. And most of what you're going to see in the lake bottom will look like that unless you're near a cliff or a ledge. So you can blame the glaciers. The glaciers were everywhere, including where the lakes are now. The lakes didn't form until after the glacier melted. So all of that area was under glacial ice, and the glacier dropped off the rocks it was carrying with it. But they've been ground and tumbled somewhat to round them off. So they're here, there, and not everywhere, but almost everywhere. And yes, they can be pretty hazardous.
Absolutely. Yeah. More often than not, our poor Winnipesaukee biologist is the winner of that award, just, because they're on one of the tougher lakes to navigate.
Yeah.
Well, excellent. Thank you so much for being here and presenting and answering all of our questions. Really appreciate it. Thank you to everyone who attended the talk tonight. And just a reminder that this series is ongoing, so we will have talks through the end of August every Thursday evening at 7 p.m.
Right, and I thank everyone too. I can't see you, but I appreciate your joining in.